Hello, Mathemaniacs. It's the Math Edumacator here, and welcome back to another show where we talk about infinity, the biggest number. Well, it's not actually the biggest number. It's not infinity isn't a number. It's a concept. It's the idea that no matter how big a number you come up with, there's always going to be a number that's bigger. Let's say that the biggest number that you knew was 100. Okay. Well, all I have to do to make a bigger number is I just have to add 1 to it, and now I have a bigger number. Or I could multiply that number by 2. So now I've got ways I can make a number bigger no matter what that number was to start with. No matter how big you make your number, you can always make one that's bigger. Now, infinity is a pretty odd concept to most people because we live in a finite world, a world that's not infinite. Even if we took something that seemed beyond counting, say like all the grains of sand in the world, then we could, give it enough time, count them. We could eventually go, okay, here's 1, 2, 3, 4, and eventually we would get to an end. We would be able to count them all. That's not, even the grains of sand in the world aren't infinite, they're finite. And so the concept of infinity is something that's really odd. It's something that's very strange. It's hard to wrap your mind around. And especially if you start treating it like a number, then things get really weird really fast. So we're going to talk about some examples of that in a little experiment that I call the infinite ball problem.
So here I am, standing outside of a room. Now inside the room, I have my assistant, Billy, and with me, I have a box filled with infinitely many golf balls. And yeah, that's infinitely many, I promise. So at 11:59, I throw in the golf balls, which each have a number on it. Throw in balls 1 through 10. And I also do this instantaneously. I had to slow down the footage for you to see here, but I threw them in instantaneously, so it didn't take up any length of time. So Billy on the inside is receiving all of these balls, the balls 1 through 10. And once he's received them, he immediately throws ball number 10 back out. So again, this is all happening instantaneously. There's no actual passage of time here that in order for this experiment to work properly. So ball number 10 comes back out. Now 30 seconds later, I throw in balls 11 through 20 in the same manner. Then he throws out, once he receives them, he throws out ball number 20. Which I then catch. Next, 15 seconds later, balls 21 through 30 go in. And once that's done, ball number 30 comes back out.
So at each phase of the experiment, we have 10 balls go in and 1 ball comes out. The next one would be balls 31 through 40, and 40 comes out. Then 41 through 50, and 50 comes out. Then 51 through 60, and 60 comes out, and so forth. At the same time this is happening, the time between each of these steps gets shorter and shorter. Each time gets cut in half from the previous one. So from what we initially started, we had a 30-second gap, and then a 15-second gap, and then the next one would be a 7.5-second gap, and so forth. We keep cutting that amount of time in half. So we need to talk a little bit about what's actually going on here with the time. The time is an example of something called a geometric series, where we're looking at something which allows us to actually do infinitely many steps of something, but have it take place in a finite span of time. So an example of this is if you are, walking a certain distance. So on a ruler here. So if you start over here, then you're trying to walk from here to this to over here. Okay. So before you can walk that whole distance, then you have to walk halfway. So you have to walk from here to there, from here to there. And then once you're here, now, before you can walk the rest of the distance, you have to walk halfway. So you have to walk from here to there. And the next distance, you then have to walk from here to there, halfway. You go halfway and halfway and halfway and halfway, and you'll get very close, but you'll always be missing a little bit. However, if we were to actually do this infinitely many times, then you would actually be able to reach that whole distance. And so you've taken these infinitely many steps to go a finite distance. And we're doing the same thing with time. We have a 30-second gap, and then a 15-second gap, and then a 7.5-second gap. And the gaps keep getting smaller and smaller and smaller and smaller. But because of the way the series works, if you add them all together, you get 1 minute, even though there's infinitely many of them. So the real question is, how many balls are in the room when the experiment is done, which would be at 12 o'clock, 1 minute after it started? You've thrown it infinitely many times. So all the balls, which all have, there's a ball for every natural number, have all gone in the room, and some have come back out. So the question is, how many are still in the room? Well, there's going to be infinitely many balls still in the room, because the only balls that were thrown out were balls that are all multiples of 10. You have 10, 20, 30, 40, 50, 60, and so forth. So what's neat is that even though we started with an infinite amount of balls, we've kind of had to break that into two pieces. But each of the separate pieces is infinite as well. Now, the idea of an infinite amount of things being broken up into two infinite amount of things, that's not really that's not too surprising. Because if you think about all the natural numbers, you can break all your natural numbers up into odd numbers and even numbers. Now, both of these sets are also infinite, because again, anytime you have, think of the biggest even number you can think of, all you have to do is add 2 to it, and you have another even number. And the same thing with odd numbers. But the really interesting thing is that in our case, it seems like that the two sets we have should be different sizes. That the set inside the room is 9 times bigger than the set outside the room, because for every 10 balls we threw in, only 1 came out. So it feels like there should be 9 balls in there for every 1 we have out here. But that's not the case, because you can't treat infinity like a number. If we had stopped at any point before throwing in infinitely many balls, then that would be true. We would have 9 times as many balls in the room as we do outside the room. But because we carried out the experiment infinitely many times, that's not the case. It's the same amount both inside and outside. But now we're going to really mess with your head a little bit. By changing the circumstances of the experiment just slightly, we can drastically change the results. Here's how.
Just like before, on the first step we throw in balls 1 through 10, on the second step balls 11 through 20, and so forth. And we cut the time in half between each step, just like before. However, this time, instead of throwing out ball number 10 on step 1, we throw out ball number 1. Instead of throwing out ball number 20 on step 2, we throw out ball number 2, and so forth. The number of the ball we throw out is the same as the number of step that we're on.
So the only thing we've changed is the number of the ball that gets thrown out at each phase. Instead of being multiples of 10, you start at 1 and you just throw out 1, then 2, then 3, and so forth. So when I ask the question, how many balls are still in the room, now we're going to have a slightly different answer. The answer is 0. There are no balls left in the room when we do it this way. And you might say, well, how can that be? We threw out the same number as we did before. we threw out infinitely many balls in the first experiment, and we threw out infinite balls in the second experiment. So what's the difference? And again, that's true, but it all has to do with the labeling. Because if I'm starting at, if the balls I'm throwing out start at 1 and go all the way up through the natural numbers, then what that means is that all the balls are slowly getting thrown out. I'm starting at the beginning and slowly going through all of them instead of just kind of skipping around. So even though the balls are getting thrown in 9 times as fast, eventually, and again, if we stop at any point, then there would still be many more balls inside the room than have been thrown out. But because I've done it infinitely many times, I can actually be certain that I've thrown out every single ball by the end, because every single ball is in that lineup, and eventually we get to it and we throw it out. And not only that, but I can actually tell you exactly when it got thrown out. If I choose any natural number n for and the ball represented by that number, then that ball was thrown out this many seconds after 11:59. So for example, ball number 1. Well, ball number 1, we have 1 minus 1, which is 0. So 2 to the 0 is 1. 1 over 1 is 1. 1 minus 1 is 0. And 60 times 0 is 0. So that was thrown out exactly at 11:59. Then, if it were ball number 2, then we would have 2 minus 1, which is 1. 2 to the first power, which is 2. So 1 over 2. 1 minus 1/2, which is 1/2. And 60 times a half, which is 30. So 30 seconds after 11:59. So even if I picked a really big number, then let's say 100. So 100 minus 1 is 99. 2 to the 99th power is a pretty big number. Then we have 1 over 99. And 1 minus 1 over 99. So that's going to be, let's see, it's going to be 1... That's going to be 98 over 99. So something that's almost 1, but not quite. And so that number that's almost 1 times 60 is going to be something that's very close to 60. So probably on the scale, probably be about 59 point something. Well, that's something that is less than 60. So the idea is that as long as it's less than 60 seconds, then it would have gotten thrown out because it happened before 12 o'clock, and 12 o'clock is the end of the experiment, because all those time periods add up to 1 minute. So as long as it happened less than a minute after 11:59, it got thrown out. And so no matter which ball it is, I can determine when it left the room. So that's the infinite ball problem. Hopefully it gives you an idea of some of the interesting things that happen with infinity, and I will see you in the next video. Bye. Want more education? Subscribe to the official Math Edumacator YouTube channel and follow us on Twitter at Math Edumacator. See you next time. Oh, and have a totally radical day.